Okay, thank you for the presentation and the invitation about the presentation. So the topic for today, I combine two systems, steel systems, together because there are some similarities between them. Both of them are some research project I've been doing for a while. So I believe most of engineers are not familiar with or not aware of these systems. So some of you may know, but so the presentation today, I won't focus too much on the technical part, just simply more focused on introduction and to introduce you about the system and what's the advantage of using these systems for your project. So the truss, I believe most of you probably designed truss previously. The feature of the trusses is that it can go very long span. In general, most of the trusses we design is for gravity load system only, and we don't typically design a truss to carry lateral forces. So the question is that because the long span, we know we like long span, lots of space to be used. So the question is, can a truss system be long span and at the same time carries both lateral forces and the gravity? The answer is yes. I'll give more detail. And why we go long span? Because there are many industrial sport venues or even residential buildings. We like to have long span because more economical or the open space for architect to use. Especially there are some requirement up to about 90 feet long. So in earthquake region, but not only for earthquake, but for wind load, we also want some long span structures. But typically for moment of a lateral force resistant system, for example, like moment frame, if you see down the image on the right, the moment frame, typically we cannot go more than about 30 feet to 30 feet. Spend more than that, otherwise it becomes less economical. The beam becomes very deep. Brace frame could be a candidate, but usually it won't go more than 30 feet, 20 feet in span. Plus the braces can occupy the space. So on the other hand, we could use a long span structure. It's a lateral force system. So this truss has very long span. It can carry gravity loading and also can carry the forces. So there is a system called the Spatial Truss Moment Frame System, currently in AIC scientific revisions. It was added since 1997 based on research in the 1990s. So this system, of course, I'm talking about earthquake, but those systems could also be used for wind load. It has been used already in, for example, in Chicago and other places. So this system, if you see the image, has a feature that called spatial segment. It's a spatial segment. That's where that energy dissipation occurs for on the earthquake forces. Members outside this spatial segment will remain elastic. So that's a feature. And it's pretty much like a structural fuses, if you heard that before. So there are two types of those spatial truss moment frame system. One is on the right side, you can see that on the right, within the spatial segment, there are some diagonal members. So these diagonal members will increase redundancy. Energy dissipation occurred through yielding buckling of these diagonal members. But most importantly is the plastic. There is a plastic at the end of the core member. We use that discipline. On the right side is we call the ferrite panel for the spatial segment. In many cases, engineers prefer this format with this layout because they're more open. So I'll give you some examples. The system This is one of the structures using spatial truss movement for San Jose International Airport. But this is not long span. Okay. I will give you the introduction of STMF, then I will discuss long span. And there are some other recently built spatial truss movement in California. So I got those photos from some engineers. So you can see the spatial segment. This one, there's a diagonal member in the spatial segment. There's another example. Also, I want to show the big opening here within spatial segment. So we can use that to pass through those utility duct. Now, how this system resists lateral forces? And there's a short animation to show that. So on the lateral forces, and those colored one is where the energy dissipation occurs. The other part, the gray regions, will not yield. So how do we guarantee that those kind of systems, those kind of magnets are going to happen? So this is through a ability and a capacity design approach. I think we know, we learned this from our mechanics courses, that steel is very ductile in tension. So once the steel is stretched beyond yielding, the force will increase too much, but the deformation can keep increasing. That's we got that. And this is one example. We test a core member with some detailing. On the cyclic only, these loops we call historical loops. So this member, the core member, is cycled up, and you see those dark regions in the
I can't hear you anymore. Am I the only one not able to hear?
No, I can't either.
Yeah,
Neither.
yeah. It looks like his screen is frozen.
I can neither.
Are you still there? No.
Is he talking to himself now? Anybody hearing me?
Yes, but we can't hear Simon anymore.
fails. Entire system fails.
Yeah. Okay.
Okay, so
Are you
on
back?
the other hand,
Simon, we lost you for a minute there on the previous slide.
previous slide. Okay, let me go back. This one?
Yes, you might consider turning your video off in case it's a connection bandwidth issue, and then that way we at least have your sound.
Yeah, that's right. Okay, so let me just repeat this one. And my slides mostly images, so I try to go slow. So I hope you that slide can be easily understood. So the plastic is a region that still going to yield under cyclic loading, large displacement reversal without losing its strength for this plastic. So this is important for earthquake design. So this is for the ductile member. The ductile member I'm going to use for discuss this capacity design approach. So the capacity design philosophy is used for all the seismic systems. Okay, not unique to STMF. So this is a chain with different links. Every link is under the same force. Assuming the ductile link is stronger, let's assume it's stronger than the brittle link. So the brittle link gonna fail first because they are carrying the same force. So to avoid any brittle link from failure, because when any link failed, system failed. So we make the ductile link slightly weaker. You see the graph under this thing. The ductile link is weaker. The brittle link is stronger. So that way, the force in the system will never go beyond the strength of the ductile link, which is okay, because when the ductile link yields, it elongates a lot without failure. So that way we control the system with the ductility. With one link, we can control the entire system to make sure the system is ductile. So this is called capacity sine velocity. So two things. One, we have to make a link yield ductile. Second, we have to make other links stronger than the ductile link. So that's the idea. I want to show that this is a testing we did a few years ago. This is only 30 feet long, the full scale. So we're using this philosophy. We make sure that the ductile link is in the spatial segment. The member outside the member. Let me show the testing. So we increase the displacement gradually. And you probably can see there's a dark region at the end of the cord. That's the class hinge that I just discussed. And any member outside, you see that there's the whitewash is still there. So meaning there's no yielding outside spatial segment. Okay. So this is the front view. I just want so this might be more clear. Very short clip. And you probably see the four corners start yielding. And but remember outside totally fine. Okay. So for the connection, there are two different ways to do that. And the truss can be welded to the column by a big gusset plate. The truss can be prefabricated and welded on site with a joint. Or the other way is use the end plate connection. This is another way to do that. And end plate connection can just follow the AIC design guide for end plate connection design. There's a design example given by AIC design manual to show how to design this. So there's different ways to design the spatial segment. This is we add two intermediate vertical members. So those two members actually gonna fail yield earlier, and they can be replaced at first grade. Plus, those two members will increase the strength and stiffness of the entire truss. You see the yielding in the vertical member occurred first. Then the core member also yield. So this allows us to replace the vertical members after some earthquake. And eventually rupture, because that's on a very large displacement. Another type is used called buckling restraint braces. Some of you may have heard this. This is new type brace. It never buckle. It yield in both tension and compression. That's why it's called buckling restraint. So we can use the truss to discipline the energy as well. we may see the deformation of brains, and that's large axle deformation, some yielding in tension and the compression. There are some part yielding in the truss as well, but those are well controlled, so no yielding outside the spatial segment. Okay, so eventually, part eventually failed, but so now let's look at the long span. So once you know the STMF and its mechanism, so the challenge in STMF with very long span, for example, 90 feet long, is the axial force. So the axial force for long span in the core member becomes much larger, and because the truss is much longer, the gravity loading effect become much obvious. And this is similar to the column under high axial force. So we know that the column's ductility or column strength reduces once the axial force increases with the PM interaction, remember. So to the study with this extensive analysis, this is a prototype building provided by engineer in Seattle. This is a one-story building with 90 feet long span STMF, and there's nothing in between these two STMF to carry lateral forces. And there's also no other system in between to carry gravity load. So the entire gravity load is carried by STMF, and the entire lateral forces is also carried by STMF. So the STMF to carry both forces simultaneously. So we designed several different layouts. So here I just remind you that when the span length increases, the moment increases, the axial force increases as well. And also, according to AIC 341, no major gravity loading can be applied within the spatial segment, because the spatial segment is the ductile member we want to have. We don't want to carry both the gravity loading and high lateral forces. But the gravity loading can be carried by other part, the other part of the truss. So through some extensive analysis, I show some final analysis. First, we calibrate this result, and then we apply different magnitude of axial force, tension, and compression. You can see that the nonlinear final analysis can simulate the buckling on the axial force. So I just quickly summarize what happened. So the upper part is about the core member on the high. When the alpha increases, axial force increases, axial compression increases. So we see the strength becomes smaller, and the most important is the ductility dropped a lot. From left to right, you see the shrink of the loop, meaning that the core member is going to fail quickly after the field cycle. And the lower one is the axial tension. Although tension is less detrimental to the behavior ductility, but it still reduces ductility to a certain extent. So that's the critical. Based on the research, some additional loss analysis, so we propose that as long as we limit the axial forces in the core member, we can use the long span structure. Now I'm going to bypass all the analysis results to give you a conclusion. So there are a few publications to show the result. In AIC 341 or TC9 meetings, we had a proposal to revise STMF provisions based on those research, including a 90 feet long STMF. Currently, we can only use up to about 65 feet long only. So this proposal is likely to be considered in the next round of AIC 750. Not this coming 2022, next year. Okay, so next system is the Staggered Transfer System, STF. This system, some of you may heard that already. As far as I know, there is one STF is in Irving, in Dallas region, maybe more, but I'm pretty sure there's a one there. So this system actually was developed in MIT in 1960s. It's mainly to use to compete with the concrete system. For example, the post-tension flat slab system. So those concrete systems can be built very quickly, and there's no beams there. So you can have a much smaller story height, save space. This system, currently no other steel system can compete with those flat slab system in terms of story height for residential buildings. So this is one of the candidates. AIC really like the system. Unfortunately, cannot be used for earthquake region yet. This is also not in AIC's site design provisions because there are lots of things we don't know. It has been built in non-seismic region for high-rise buildings. So let me quickly give you a summarize the advantage of this system. So you can see why it called staggered truss. The truss in upper floor and the lower floor, they are not in line, so they can stagger. So you see the highlighted region, there is a wide column-free space there, so can up to 80 feet in this transfer direction, in the horizontal direction. But out of plane direction, the truss direction can also go to about 60, 70 feet long. So in both directions, there are very wide space for architect to use. There's some other advantage because the column lines are only on the perimeter, and so it will reduce the foundation work a lot, and also reduce the superstructure weight and the floor height. The floor height and typically is about 8 to 10 feet only. 8 to 10 feet only. Some other advantage by, for example, this can be constructed very fast. You can see the image here. Day 11, they almost finished 4-5 story already. So fire resistant, some other things. You can build any weather. So this summarizes the features. I want to spend a bit more time here. You see on every truss is a floor height. Every truss represents the height of the truss is the floor height. So in between the staggered truss, there's a non-truss level, no truss at all, because the truss staggered. So this creates some problem that this story becomes very weak or more flexible. Plus, if you see the column actually, the strong axis is oriented in the longitudinal direction for the moment frame. And along the truss direction or the transfer direction, the column is bending along its weak axis. Okay, that makes things even worse. The diaphragm system conventionally is the hollow core plank, because hollow core plank can go very long span, pre-stressed, pre-cast hollow core plank. So all these plank are also prefabricated. So that's why the construction can go very fast. Okay, so why there's issue with this system? The major issue is about the force transfer path. So we see that the vertical truss is staggered, right? Not only the truss is staggered, but the force transfer is also staggered. That I'm using this very simple model to show that. For example, in the upper floor, there is a force applied, 1P applied. So assuming the lower floor consists of 3 moment frames, they're equal, totally equal, stiffness, transfer equal. So roughly the force will be transferred from the upper floor to lower floor by a ratio about 30%, 40%, 30%, roughly equal. Okay, no problem. But in the staggered truss, we see the image on the lower side, and the staggered truss, because the trusses are staggered, and right below the truss above, there is no truss, very flexible. So we know the force goes to the stiffer member, right? From structural analysis, we know that. So the force on upper floor will have to go to the two trusses on the exterior and the lower floor. So how that gonna happen? That will only happen when the force had to transfer across the diaphragm. Okay, so this staggered truss caused the force to be transferred across the diaphragm. So you see the ratio 45%, 45%, and 10% only underneath. So I will show this video that if I have more time, but let me just give you the illustration how the force transfer for earthquake forces. So we know earthquake force is inertial force coming from the mass of all the elements there. So everything in the system has inertial force. So this has to be eventually transferred through structural members, diaphragm, down to the foundation. So let's start from the top. If we look at the inertial force has to be transferred to the lateral force system. But for this one, let me see. This one is flexible. This one is stiffer. This one is flexible. So the inertial force automatically, majority of them will transfer to the staggered truss, not to the non-truss level. Okay. And once they go down, it will not go down because below that is a flexible non-truss. So it has to go across the diaphragm plus its own inertial force in this diaphragm. So it on top, okay, on top, the force from upper floor, there is inertial force on the lower floor to become larger and go to this truss. Again, it will not go down because below that is more flexible. So you go to another and plus additional inertial force. So force become larger. You can see that become larger and larger, larger and larger. Okay. So the truss itself is okay. We can always design truss stronger enough to carry those forces. But the problem is the diaphragm and connection, meaning the connections carry ever increasing forces. It's different from compression system. Compression system, every flow the connection forces, the difference is not that large. Okay. However, for the STF system, the upper floor and the lower floor, the connection can carry completely different magnitude of forces. So that's the issue with this system. So that's one issue. There are some other issues. For example, there's almost no research in this area. We're probably the only one doing the research since about 10 years ago. So this is some fundamental element analysis to show that there is a concentrated deformation or stress in the connection. So just to check how strong the connection, so we did some field testing. The connection conventionally used is this, very simple. And this is a truss core, bifold truss core. And on top of this one, there's our plane, okay, on top. So how they connect together? A shear stud, just like the regular shear stud we use for composite deck. And they ground it on side. Sometimes they put a rebar in between, just to bond them together. And they ground on side. The ground not going all the way through, but they put enough ground to ground the joint. And that's what's been done typically for STF. So we want to know how strong is this connection to take shear forces. And we know shear force can be very large. And I just want to show quickly some testing and how we did it at UT Arlington. So we follow the practice, and this is the testing setup. The second testing we did, the first test is monotonic, so I won't show here. The second test is cyclic testing. So what we found is that the ultimate loading is about 57, 55 kips, and the shear stud failed. Okay, so it seems to us that we can increase the shear stuff to increase the shear strength. So the second, another specimen, we increase the shear stuff from 4 to 6, and also we observe there are some bond cracking on the rebar. So we just make the hook to increase the bond. Surprisingly, the strength did not increase. It's still about 55 kg. The reason being that when we increase the strength of shear stuff, the hollow core slab still failed. There's some damage. You can see that severe damage, uncontrolled damage in concrete. Another thing we try is put the topping on top. Usually for the precast pre-stress member, we put a topping about 2 inch at the length of the surface. We'll see if that helped. It did not. The composite actually failed quickly, and the failure is still controlled by the hollow core slab. So from this study, we see that the connection has some limited strength, cannot go more than something. There's upper bound. So next step is what we use analysis to find out what could happen in the actual building. Okay, in this, we just start from a 6-story building. We can find out demand analysis is about 9.5. Okay, for the capacity we got larger. That's okay, but for high-rise building, this demand will be much larger, but capacity will not be increased. So there will be issue there. Plus, the damage is in concrete is relatively uncontrolled. We don't want to fail in joint because it's very hard to repair. And plus, in the testing, we did not apply gravity loading yet. So the damage could be much severe than we observed in testing. So considering this factor, we decide to propose another system in order for the force transfer reliable. Is the horizontal truss system. We don't use hollow plank. We just use the steel horizontal truss. This kind of truss system has been used in some steel system for some industrial buildings. And usually it's very lightweight, but this one will be slightly heavier because it has to transfer the cumulative forces from upper floor all the way down. The truss is very efficient to transfer little forces because it can transfer through axial forces. It's very efficient. So we don't have to use very large metal. So we did some modification here. Sorry, this can be a little complicated. So now, if you remember, the hollow plank previously is going this direction, the longitudinal direction. Now we don't need that anymore because we don't need hollow plank to transfer little forces. We put in direction. So they don't have to transfer cumulative forces. They just sit there as a floor, that's all. And the cumulative forces transferred by the horizontal truss. And here there's a gap. In reality, we're gonna cover that in case there's a fire, there's smoke, will be stopped. Another important thing is that we're using the STMF. You still remember that the STMF. We're using the STMF, the spatial segment, to dissipate energy. In the conventional design STF, there is no defined yielding member to dissipate energy, meaning that yielding can happen anywhere in the columns, the joint, in the truss member. So we are using this similar concept on STMF. We borrow from there, and we'll put the horizontal truss away from the spatial segment because we don't want the spatial segment carry both the lateral forces and the gravity load. This can be easily done by the horizontal truss. There are some other issues. The C system, those are the reasons why the system is still not used in vertical range. And conventionally, the central frontal panel, that's for the corridor, typically for corridor, has a very large deformation. So once we change that to the spatial segment, we can reduce the rotation demand. Just remind you that what happened to the spatial segment in STMF. Another issue is the column. I briefly discussed that the column is oriented in its weak axis along the transfer direction or the truss direction. Plus, this non-truss level is very flexible. So we see from analysis this column kink a lot. So the different approach to fix that problem, and two approaches I show here is that, for example, use some vertical member with some kickers to increase the stiffness. So from analysis, you can see that the lower one is the conventional one. And you see the large column kink here, column fading. Anything in red color meaning yielding severe damage. There's a huge deformation here. Typically, the member cannot carry that. Once we modify the layout, the yielding region is confined. We are confined in the spatial segment only. And the rotation is not that large. The column does not kink anymore. So the last 2 or 3 slides, I want to show that some nonlinear time history work. I skip a lot of steps here. First, we decide the system using AC7 earthquake forces. And then we have those calibrated spectrum. Then we run this nonlinear time history analysis earthquake. The first is the conventional 6-story conventional STF. I want you to look at those regions in red color. Those ones in red is where damage occurred. And you see that's in uncontrolled manner. This simulation is very slow. Of course, every earthquake will be way quicker than this. Some members start changing colors. Eventually become red. That means damage occurred there when yielding occurs. There's some column yield and damage, and there's huge deformation in the central panel. That's huge deformation. Actually, it will fail. And many of the columns also kink will fail. It's likely it's going to collapse under the large deformation. Okay, so the next one is the modified. Based on all the modification I discussed previously, the horizontal truss and all those spatial segments and kickers and other. You see this on the same earthquake. The yielding is well confined in the spatial segment in the core member and the vertical member, and the rotation is not that large compared to the previous one. And there's no yield in the column. So this is what we want to achieve, that the yielding damage in the member is well controlled in some locations. We know we can repair that without worrying about other locations being damaged. So the last one illustrates the 20-story estimate. Of course, we only run the ground motion in one direction only. The other direction is moment or bracement, and that's the convention we use. We don't have worry too much about that. So high-rise building has different features. For example, the higher moment effect. So that's what we want to see how for this a bit slow because it takes a lot of computation power. This is also modified, so our intention to confine any yielding or damage within the spatial segment. So in general, we still see that performance is under control as intended, and no yielding columns, and all the yielding is in the spatial segment. So thus we solve our problem. So we're planning to do some more research on some large scale testing, restrictive testing. If we're gonna fund AIC is very interesting because in California, right, for example, in California, they cannot use this system to compete with other system. The big market there is about low to mid-rise buildings, residential buildings, office buildings, with lots of people. Yeah, they need low span structures. Yeah, can be constructed very fast, but still industry they don't have a candidate to compete with post tension flat slab system. They use that very commonly in California. Missy, do we still have about 2 minutes?
Yeah, we have until 1, so we have about 19 minutes left.
Okay, basically I finished. So I just I want to go back to the slide I promised to show about the load transfer path in STF. I feel that it's probably better to have animation, so we spend some time to prepare this animation. So for people to understand the system a bit more. For many years, there's a misunderstanding because there are analysis were done by using two-dimensional analysis, which is not correct. We see that the force transfer in different directions. It cannot use a 2D system. So this is used for to illustrate this idea.
The video is frozen for me. Is it working for everyone else?
No, I'm not seeing anything. It's frozen.
Nope.
And can you try restarting it again?
Floor. So once the force transfers across the diaphragm, and the additional inertial force acts on top of this inertial force, it becomes larger and larger. You can see that now becomes 300, more than 300 kips right now. And all the force actually goes through the joints. So that's pretty good. Eventually go down to the ground. But through the process, it might have damaged some connections I showed that in the testing we did previously. In the wind region, for example, in Texas, I don't think there's issue. You don't have those huge earthquake forces and only wind load. So this system should be a very good candidate to be used. I think there might be some reasons that either engineers are not aware of this system or they're not familiar with this system. So this system is still not that popular, although AIS really want to promote this system. But hopefully through more research and more publications and more introductions like this opportunity, so we see more of those systems being built. So that concludes my presentation. Thank you.